Greetings to everyone. So today we are going to discuss certain topic of that is design problem related to welded plate girder and design of intermediate stiffness. Okay, let us go on to the topic right now. So first we'll write the problem. Okay, design a welded plate girder of 24-meter span and laterally restrained throughout. It has a support. It has to support a UDL of 100 kilonewton per meter throughout the span, exclusive of itself weight. Now design the girder with intermediate stiffeners. Okay. So consider Fe 410 grade of steel are used and the Fy value of steel is Fe 250 megapascals. Okay, design the cross section and end connections. Okay, now let us move on to the solution part. So first, what are the loads? That is total load is going to act that we have to calculate. Okay, step one, load calculation. So here they have mentioned that the load of 100 kilonewton meter is acting. Okay, so let us go on to the self weight. We have to consider the self weight also. So self weight of the girder formula is WL by 400. So W is nothing but our load, that is W is equal to point load we have to convert. Okay. So here they have given us UDL. So that UDL into total span, we can get the load. So 100 into 24. Okay. That is our W. So 100 into 24 into 24 divided by 400. So it becomes 6 kilonewton per meter. Okay, sorry, it becomes 144 kilonewton. Okay, 144 kilonewton. Therefore, I need in terms of kilonewton per meter. Okay, so what I have to do? I have to divide this value by the span. So self weight of girder per meter length. Okay, so 144 divided by span length 24. So it becomes 6 kilonewton per meter. Therefore, total load is equal to load acting on the girder is 100 kilonewton per meter plus self weight of kilonewton per meter. So it becomes 106 kilonewton per meter. Therefore, therefore factored load acting on the girder is equal to total load multiplied with factor of safety. So total load is 106, factor of safety value is 1.5. Okay, so it became 159 kilonewton per meter. So this is our load acting on the structure. Now we have to go for step 2, that is calculation of bending moment and shear force. So calculation of bending moment and shear force. Okay, so first one, calculation of bending bending moment. Okay, so bending moment m. So here it is simply supported with UDL. So the moment value is becomes WL squared divided by 8. Okay, so here the W is 159 kilonewton per meter. So 159 into L squared, 24 squared, 9 kilonewton. Okay, so this is simply supported by with UDL throughout divided by 8. So it becomes 11,448 kilonewton meter. Then shear force V is equal to WL by 2. So 159 into 24 divided by 2. So it becomes 1908 kilonewton. So this is the value of bending moment and this is the value of shear force. So now we have to design the sections, okay, for withstanding these bending moment and the shear forces. Okay, let us considering that. So first of all, we should go for a flange design. Okay, design of flange. So the girder consisting of flange, web, and along with that we have to go for end bearing stiffness, which means with respect to cross section I'm telling. So this is our plate. So here this is our flange. Okay, na? So this is our end bearing plates, and here we are going to give intermediate bearing plates. Okay, so like that. So these two are end bearing, stiffeners. Okay, and these two will be intermediate stiffener. So we have to first we have to design the main member, then after we have to go we have to design the main member and we have to check it whether it is safe in shear and bending moment, that we have to check it. And let us go to the design of end bearing stiffness. Okay, now so whether this bearing stiffness is safe in shear or not, that we have to check. Safe in shear and safe in buckling, so those things we have to check it. Similarly, we have to move on to intermediate stiffeners, whether after selecting the section, whether it is safe in shear and buckling, that we have to check it. So these are all the constraints. Now let us move on to the flanges. Okay, so let us assume this is step 3. Okay, assume flanges will be taken care of bending moment. Flanges are taking care of bending moment. Okay, now so that area required for flange. So the formula is area flange is equal to moment into gamma nz divided by Fi into z. Sorry, Fi into d. Okay. So if I need d value, then I have to design the web plate first. Okay. Uh, Let us move on to the design of web first. So first we should move on to the design of design of web plate. Okay, so design of web plate. So we have to assume that web is going to taken care of. Is taking care of shear. Okay. So let us consider that with respect to limit state and serviceability requirements. Okay, from page number 65 of IS 800 2007. Okay, so d by dw should be less than or equal to 200 times of epsilon. Okay, this is with respect to serviceability condition. Okay, similarly, d by tw value should be less than or equal to 345 times of epsilon f square. Okay, so this is with respect to flange buckling criteria. Okay, so now we are going to substitute this. So epsilon, we all know that root under 250 divided by fy. Okay, so both are same, 250 by 250, it becomes 1. So 200 are less than 345. Okay, so based on that we are going to. Okay, so we have optimum depth formula. Optimum depth of the plate dw is equal to m z into k divided by fy power 0.3. So whereas mz is equal to 11,448 kilonewton meter. Okay, and fy is equal to 250 newton per mm square. They have given. And k value. So k value we are going to assume as 180. Therefore d is equal to, thickness of web is equal to, depth of web is equal to, so what is the formula? Mk into z. So mk into z divided by fy. Okay, whole power 0.33. Then the value becomes so 1872. Okay, so approximately now we are going to take some 2000 mm. Therefore thickness of web, okay, is nothing but mz divided by fy into k square. This is the formula, power 0.33. Then it becomes 250 into k square. So k value is 180 square. So it becomes power 0.33. Then the value of thickness of web becomes so 10.95 mm. So we are going to say 10 mm. So therefore provide web plate of size 2000 mm by 10 mm. So this is depth of web and this is thickness of web. Okay, let us go in with this section. Next step 4, that is design of flange. Design of flange. So for the design of flange, we already said that the formula AF is equal to mz into gamma m naught divided by Fy into d. Okay, so d is nothing but depth of web. So 11,448 into 10 to the power 6 into gamma m naught value from table 5 is 1.1. Fy value is 250 Newton per mm square. They have given the depth of web, we have arrived at 2000. So if I'm going to substitute this, I can get the value 8 into 10 to the power 6 into 1.1 divided by 250. So the area of web required, area of flange required is 25,185.6 mm square. Okay. Now I am going to assume. So assume width of flange is equal to 0.3 times of depth of girder. Okay, so 0.3 into 2000, so it becomes 600 mm. Okay, then thickness of flange, TF is equal to area of flange required divided by breadth of flange. So area of flange required is equal to 25,185. 25,185.6 divided by breadth of flange, we got that 600 mm. So if I'm going to substitute this, I can get the value of, so it becomes 41.976, say 50 mm. Okay, therefore provide flange plate of size 600 mm by 50 mm. This is breadth of flange and this is thickness of flange. Okay, now we have arrived the sizes. So here so this is our breadth of flange is equal to 600 mm. Thickness becomes 50 mm. And we have the web. Okay. So web of thickness 10 mm and the height of web is equal to 2000 mm. So this is where we have arrived right now. Now let us move on to the remaining part, that is with respect to post critical method. Post critical method. Okay, let us proceed the problem. So first step 5, requirements for intermediate stiffener. Okay, so here we have some constraints with respect to our IS 800 2007. So here we are having from page number 60. Okay. Yes, here. Okay. With respect to C by D value only, we are going to so here we can have C by D value. So this is simple post critical method. Okay, now. So here with respect to C by D value only, we are going to have everything. Okay. So C by D value we can have maximum, that is greater than less than 1 and greater than 1. So greater than 1 means up to 1.5 we can take. So by using that we are going to have our remaining constraints. From page number 60 of IS 800 2007. So C by D value we are going to use. Okay. So C by D value is less than 1 and greater than 1. So greater than 1 means it should be less than or equal to 1.5. So this is the constraint. Okay. So let us move on to this. So C by D is, we are going to take some 1.4 value. Therefore C. So C is nothing but the spacing between the stiffeners. Okay. So this is end bearing stiffener and this is our end bearing stiffener, and in between that we can have our intermediate stiffeners. Okay. So the spacing between the stiffeners is nothing but C. So D is nothing but the depth of section. Okay. So C by D is equal to 1.4 we have taken. So D is equal to 2000 we can take. Okay. Is equal to 1.4. So D is equal to depth of web I'm going to take. So it is 2000. Therefore spacing C is equal to 1.4 into 2000. So it becomes 2800 mm. So if it is 2800 mm, that is spacing spacing between the stiffeners is 2800 mm. Then how many stiffeners we required? So number of stiffeners. Therefore, number of stiffeners required is equal to total span divided by spacing. So total span is 2000, that is 24 meter. So 24,000 divided by C, 2800. So it becomes, so 8.57 numbers it is coming. Okay, now. So we have to give in round up manner. So we are going to have 9 numbers of stiffness. Okay. So if it is 9 numbers, if it is 9 numbers of stiffener, then what will be the spacing provided? Okay, so L divided by numbers, so 24,000 divided by 9, it becomes 2666.67 mm. So this is the spacing we have provided. Okay, so spacing provided, spacing between the stiffeners is equal to 266.67 mm. Okay, so we have to calculate with respect to C by D value. Okay, so 266.67 divided by 2000, then it becomes 1.33. Okay, therefore C by D value is 1.33. Our condition is it should be less than 1.5. It should be less than 1.5. Hence, it is satisfied. Okay. So next we should move on to the remaining thing, that is stiffeners, shear capacity of web, moment capacity of web. So those things we are going to check it right now. So first, sorry, next, step 6. So shear capacity of web. Okay. So from page number 60. So I will share the code book. Page number 60. Okay, so with respect to C by D value, okay, C by D is greater than 1 means I have to use this KV value as 5.35 plus 4, okay, divided by C by D square. So here shear capacity formula is VCR, okay. So tau CR, the elastic critical shear stress of the web, is equal to kV into pi squared E divided by 12 into 1 minus mu squared into d by tw the whole square. So this is the formula we are going to use. So tau CRE is equal to, from page number 60, equal to kV into pi squared E divided by 12 into 1 minus mu squared into d by tw into whole square. So kV value. Okay, if C by D value is greater than 1, okay, then KV is equal to 5.35 plus 4 divided by C by D the whole square. Okay, so 5.35 plus 4 divided by 1.33 the whole square. So it becomes 14.395. So E value, we are going to assume that steel structure 2 into 10 to the power 5 Newton per mm square. Okay, and Poisson's ratio mu is equal to 0.3. So now we are going to substitute these values. So tau CRE is equal to KV 14.395 multiplied with pi squared E, pi squared into E 2 into 10 to the power 5 divided by 12 into 1 minus mu, 12 into 1 minus mu squared into d by tw, that is 2000 divided by 10 the whole square. So it becomes so KV value is 5.35 plus 4 divided by 1.33 square. Okay, 7.611, correct. 7.611. So 7.611. So the value 7.611 multiplied with. So it becomes 34.394 Newton per mm square. Once again, here I have to check it. I will share the code book. So once after getting this, I have to go for lambda W, that is non-dimensional web slenderness ratio. Then based on that value, I have to get the shear stress. Okay. So the lambda W value, I have to get it first. Non-dimensional. So non-dimensional slenderness ratio. That is lambda W is equal to root under FIW divided by root 3 into tau CRE.